Hey guys, welcome to the pre-learning for lesson 0.2, which is about biostatistics. So up here on our screen, I have the notes that you should have open. So this was the notes packet that we really started with and you've already been doing some work on. You're going to take yourself to section C, which is primarily this big chart. All about biostatistics and different calculations that you could be expected to do on data that you gather in an experiment. So we're going to go through section C, biostatistics, and we're actually going to take it all the way down to error bars. So that's as far as the video will cover today, and that is pre-learning 0.2 that you should have watched this video and taken notes to the point that I indicated before you get to class, either Monday or Tuesday, depending on what period you're in AP Bio. So let's go back to, and let me present with the new content. Here we go. Okay, so biostatistics, really, when we talk about biostatistics, we are talking about, for us, we're talking about descriptive statistics. And so you can see in your notes that you have descriptive written down. There's a little bit of space beside it. Here's what descriptive statistics really are. And you should write out to the side of that word. Descriptive stats are numbers and really calculations run on numbers that describe a data set. And so descriptive statistics, as the name sounds, describes data. There's three primary types of descriptive statistics, and you do not have to write this down because, as you will see, this is how your chart is broken down. So the first type in your first big box is descriptive stats on measurements of frequency. So we'll talk about what does it mean to measure frequency and what kinds of calculations or data can you collect to measure frequency. Measures of central tendencies are the second big type of descriptive statistics that we need to be aware of. And the last are measures of variability. Variability, think of variety and variation, so differences that exist within our data. So we're just going to kind of go through it in that order, and you're going to be able to fill in the chart as we go. So let's talk about a measure of frequency. So off to the very left of your notes, you have what's called the measure of frequency term. And in that little box over there, you should write down measures of frequency answer this question. How often does something occur? In my data set, how often does something occur? There's three different calculations that we can do for measures of frequency. And I'm thinking, let me move my, where could I be best? Maybe here. The first, and these three, honestly, y'all have been knowing these for a while. So the first type is a count. So you can see in your notes, there's a box for count and then a place where you describe what is a count. A count is really a tally, a count of times that something occurs. So I've got our tally marks up here as a reminder that tallies are counts. Frequencies are like fractions, parts of a whole. And as you calculate the frequency, your final answer will always be in a decimal. So there were 7 parts out of 10, 7 of 10. If I really do that, 7 divided by 10 is 0.7. So a frequency is going to show or indicate parts of a whole, and once calculated fully, will be given in decimal format. We can turn a frequency into a percentage very easily by multiplying by 100. And that's what I've given us here. I can't find a good place for my face. We'll go up here. This right here is the formula for calculating a percent. So you would first do a frequency and then multiply that by 100 to get a percent. So all of these are various ways that you could determine how often a particular value occurs. Let's move to the next section of the chart. And there we go. A measure of central, you know what? My face is really just in the way, so I'm going to get rid of it. A measure of central tendency. Now, there's a lot of stuff going on over here. We'll get to all of it. Don't be too nervous about it. Find in your chart where it indicates a measure of central tendency and write down this question. Measures of central tendency indicate what one number could best represent my entire data set. And so for this, measures of central tendency are, you've heard of these before, mean, median, and mode. Okay, so mean is an average. Now you know how to calculate an average, but what I want you to now know is this formula right here. X bar is the symbol for mean. So X bar equals the sum of all of your numbers, that's what X means, divided by N, which means the total numbers in the data set. So if I had a data set that had 10 numbers and I summed them all up, I would then divide them by 10. Of course, you know that's how you get an average, but I want you to pause the video here and write down this equation, only because if you saw it, it might feel like, I don't know what that means. That is the calculation for mean. X bar equals the mean. So again, the mean is equal to the sum, that's with this funny E, the sum of all of your numbers in the data set divided by the total number of numbers in the data set. All right, so let's next look at the median. The median is really like a median in a highway, the thing that runs down the middle of the road. It's the number in your data set once you have your data in sequential order. So to find the median, the first thing you're going to do is order your numbers from small to big, and then find the middle number. So in this first data set, it works out nicely because it's an odd number. So you have 3, then the median, which ends up being 6, and then you have 3 more data points here. If you have an even number of numbers, you're going to have to average the 2 middles to get the true median. So a median is going to be line them up in order, find the middle number. The mode is the number that appears most frequently in a data set. And so for that, let's look at this picture down here. If this is your data set, 639, 66593, this is a very simple elementary style of counting or tallying. Okay, there were 3 3s, there was 1 5, there were 2 3s, 1 5, 3 6s, and 2 9s. The mode of this data set would be 6. 6 is the number that appears most frequently within this data set. So those are measures of central tendency. Most likely, you've seen them, you know what they are. Maybe new to you today is this more complicated formula right here for the average. Make sure that you have written that down. Now, let's move into something that probably is new to you. So our last section here relies on measures of variance. And so find measure of variance or variability, I think is what your notes say. And really the question that these calculations seek to answer is how much spread exists in my data? Are the data points all over the place, or are they clustered around certain values? And so for this, we're going to look at 2 calculations. And the first one is called the standard deviation. So the standard deviation, and I've put this kind of into words, it's a formula that takes each data point in your data set and compares it back to the mean or the average of the entire data set. And it is done by putting values into this very aggressive formula right here, which is already given to you in your notes. So first, let's know this little symbol right here that looks like an O with a line to the side. That is the symbol for standard deviation. Some formulas, instead of having the symbol, just use the letters SD for standard deviation. But here is the formula for standard deviation. You're going to take the square root of this value. So again, we see some things that we saw in the mean formula. The numerator is the sum, that's what that funny E looks like. the sum of all individual data points minus the average of the entire data set squared divided by the number within the data set, like if there were 10 data points minus 1. So here's the great thing. You do not often have to calculate standard deviation, but you do have to understand what it means, and you have to understand how to apply it if it is given to you. And I have seen that frequently, where you have to analyze an experimental data set, perhaps you have to graph the data, and you have to understand what the standard deviation of the data set is telling you about the data. So keep in mind, this is a number, a value that is going to tell us how much spread exists in our data set. Is the data all over the place? Is it scattered all over the place? Or is it clustered around a particular number range? So before we move forward, I want us to make sure we really understand standard deviation, and we've had the chance to see some representations of it. So we're going to watch this video together. Here we go. Let's make it large.
Have we discovered a new particle in physics? Is a manufacturing process out of control? What percentage of men are taller than LeBron James? How about taller than Yao Ming? All of these questions can be answered using the concept of standard deviation. For any set of data, the mean and standard deviation can be calculated. For example, 5 people may have the following amounts of money in their wallets: $21, $50, $62, $85, and $90. The mean is $61.60, and the standard deviation is $28.01. How much does the data vary from the average? Standard deviation is a measure of spread, that is, how spread out a set of data is. A low standard deviation tells us that the data is closely clustered around the mean, or average, while a high standard deviation indicates that the data is dispersed over a wider range of values. Standard deviation is used when the distribution of data is approximately normal, resembling a bell curve. Standard deviation is commonly used to understand whether a specific data point is standard and expected, or unusual and unexpected. Standard deviation is represented by the lowercase Greek letter sigma. A data point's distance from the mean can be measured by the number of standard deviations that it is above or below the mean. A data point that is beyond a certain number of standard deviations from the mean represents an outcome that is significantly above or below the average. This can be used to determine whether a result is statistically significant or part of expected variation, such as whether a bottle with an extra ounce of soda is to be expected or warrants further investigation into the production line. The 68, 95, 99.7 rule tells us that about 68% of the data fall within one standard deviation of the mean. About 95% of data fall within 2 standard deviations of the mean, and about 99.7% of data fall within 3 standard deviations of the mean. The average height of an American adult male is 5'10", with a standard deviation of 3 inches. Using the 68, 95, 99.7 rule, this means that 68% of American men are 5'10", plus or minus 3 inches. 95% of American men are 5'10", plus or minus 6 inches, and 99.7% of American men are 5'10", plus or minus 9 inches. So this means only about 0.3% of American men deviate more than 9 inches from the average, with 0.15% taller than 6'7" and 0.15% shorter than 5'1". This reasoning suggests that LeBron James is 1 in 2,500 and Yao Ming is 1 in 450 million. In particle physics, scientists have what are called 5 sigma results.
We don't need to see particle physics, but hopefully as you watch that, you were able to kind of understand that although you don't have to calculate a standard deviation, standard deviations can tell us something about a data set that we get from an experiment. So let's talk about how we're going to interpret standard deviations. So when we look at, there we go. If our standard deviation that we calculated, or that rather is given to us, is a large number. So let's say we had a standard deviation of 50. That tells us that there is a lot of variation or spread in our data. And if you graphed it, a large standard deviation would look like this line running right down here that is pointed to with the black. Now, what is that really telling us? That's telling us that the data that we got from our experiment was all over the place and is probably less reliable and probably not going to be really great data for being able to connect the independent variable back to the dependent variable. So when we're running an experiment, we are looking actually for a very low standard deviation value. Low values tell us that there's less spread in the data. Most of the data is pretty clustered around the mean of that data set, and the independent variable is probably responsible for the dependent variable in that case. If you were to graph it, you would get this really steep graph where most of the data is clustered around this dashed line right here, which is the mean for both of these examples. So we are hunting and looking for the smaller the standard deviation, the more reliable we feel like our data is, and the more we are likely to attribute the independent variable to the dependent variable in an experiment. So standard deviation is one calculation that shows a measure of variance or variability in a data set. The other measure of variance that we're going to look at is something called the standard error. It is abbreviated SE. Really, it's called the standard error of the mean. And so occasionally I have seen in AP questions on the real test that instead of SE, they use SEM for standard error of the mean. But look at the numerator here. And the reason we covered standard deviation first is because the full calculation of a standard deviation is actually the numerator for standard error. So you would take your standard deviation and you would divide it by the square root of the number of samples in the data set. So again, we've already covered standard deviation. Let's talk standard error. Standard error of the mean is the standard deviation of the means of an experiment with multiple data sets. So basically, if we ran an experiment and we had multiple trials and we averaged the data on each of those trials, we could run a standard error calculation to see how spread out is the mean for all of the data sets. Basically, what's the standard deviation? What's the spread on all of these different means of these different trials within our experiment? And really, this part down here, this is where the rubber kind of meets the road. This standard error is used to kind of tell us how precise the calculated mean of a data set is. And it allows us to know if we can apply a small experiment with a small sample, a small amount of data, to a larger population. So standard error of the mean, again, is a kind of step up that you would calculate on an experiment that has multiple data sets within, and you're basically looking for the standard deviation of the mean of all of those data sets. And again, the purpose of it is to be able to say if the standard error of the mean is low, then you would say, you know what, it looks like we have run multiple trials, we have collected a lot of data, and what we have come to realize is that our experiment is yielding pretty constant results. The values that we're getting are pretty clustered around the mean. And so we feel pretty confident in being able to extend our thinking from this small experiment into a larger population even though we didn't run the experiment on the full big population. Now let's talk about this diagram. You have this, and it was actually mentioned in your video that we just saw. This is, and you can label it, this is called a normal distribution curve. Some of you may have seen it in math classes before and maybe called it a bell curve. And so what this is telling us is this is all of our data. Right here is the mean, right down the middle. And so if you think back to the height example, the average height of a man is 5'10" in the US with a standard deviation of, I can't remember what they said, 5 inches maybe. So one standard deviation less than the mean would be take away that value. So if we were sitting right here at 5'10" and it's a standard deviation of 5 inches, then this value at one standard deviation below the mean would be 5'5". And if we went one standard deviation above the mean, this value right here would be 6'3", maybe 6'3", right? Plus the 5 inches. And so this right here is representing a normal population curve where, and what we say in bio is that there's a 68, 95, 99.7 rule. We look at plus or minus 2 standard deviations of the mean, and that should incorporate 95% of your data points. So we're going to talk about something called a 95% confidence interval. It's somewhat connected. So remember that 95. If you go out, so we talked about if you go out 1 standard deviation from the mean, that should encompass 68% of all of your data points in your data set. If you go out 2 standard deviations, that should encompass 95% of your data in your data points in your set. If you go out 3 standard deviations, that should capture 99.7, almost all of the data within your data points if you're sitting in a normal distribution curve. Now, we're not going to get too far into the weeds on other types of curves because really we want to hone our skill on this. But I want you to know that really when we're looking at data, it's always going to, in bio, we're going to use plus or minus 2 standard deviations. We're going to be concerned with about 95% of the data points being clustered somewhere around that mean. Okay, let's talk about error bars. Okay, error bars could look like either of these 2 diagrams that I have put up. So this would be if you did a bar graph to represent your data and then you added something called error bars. So here you can see they look like big giant eyes on the top of each. This is another way of representing error bars without actually graphing a bar. This would be, imagine if this were the top of the bar right here, and then you still have your error bars that exist. So error bars can be drawn on a diagram based off of standard error calculations or standard deviation calculations. Most of the time, we will work with standard deviation calculations, making error bars represent standard deviation calculations. Bio typically, again, uses plus or minus 2 standard errors or standard deviations on our error bars. This establishes what's called a 95% confidence interval, which means 95% of our data points are going to fall within this range as long as we're talking about a normal distribution curve. So how do I actually apply an error bar? So let's say that you averaged your data, you're going to make a bar graph, and between 3 different groups, your first, let's say you had an average of 10 within your data set, and your standard deviation was plus or minus, or your standard deviation was 2. So then what you're going to do is you're going to draw your bar graph up to 10 with your average, and then you're going to take it up 2 standard deviations. Well, what is 1 standard deviation? What did I just say? 1 standard deviation in this example is 2. So if I take it up 2 standard deviations, how many do I increase it? Hopefully you said 4. So that means the very top of my error bar would be 4 notches above the average, which was 10, the top of the bar graph. So the top of my error bar would end up at 14. Now think about, what would the bottom of the error bar end up at? If the average was 10 and we dropped it 2 standard deviations, we're going to drop it 4. So what are we going to be? 6. Hopefully you said the bottom of the error bar would be at 6. So that's how we actually draw the error bars. And then we are confident in saying in that example that 95% of our data in that set fell somewhere between the numbers of 6 and 14. Here's how we use error bars. You have to know how to draw them. And so we'll do some practice this week in class on drawing them, but you also have to know how to interpret using them. And so when it comes to error bars, an error bar itself doesn't tell us that much. I mean, it tells us the potential spread that exists, because remember, they're based off of mostly standard deviation. So if the error bars are huge, that tells us that there's a lot of spread in the data set. If the error bars are tiny, that tells us that there wasn't much spread in that particular data set. But on their own, that's about it. What gets interesting is when we can start to compare groups. And so we use the error bars between 2 or 3 or 4 groups. And what we're looking at is overlap of the error bars. And so here's the rule. Error bars, again, are used to compare different groups. For us, that's primarily the control group compared to the experimental group. And if error bars between 2 groups overlap, like we see here in this top example, if there is overlap, there's not really a significant difference between the outcomes of those 2 groups. I would be really hesitant in this case to say that whatever we were testing, the independent variable, caused the results that we got. Now, this picture in the middle shows less overlap. There's just a tiny bit of overlap. Again, not significant difference. A little bit more possible room for negotiation in trying to relate the independent to the dependent variable, but still, if there's overlap, we're saying that really the data from one group has some overlap with the data from the other group. So chances are whatever we were testing didn't have a significant impact. What is interesting is if the error bars from the groups you are comparing do not overlap. And so that is this example down here. So in this example, we can see, number one, there's a very small error bar over here on this data set, which means that there was very little spread in this data. Over here, there's a lot of variance in this data. But when I start to compare the 2 groups, the top of this error bar does not get into the zone of the bottom of this error bar. There's no overlap, which tells us there's a really big difference in the values that exist within these 2 data sets. And so chances are whatever you changed between the 2 data sets really did something, really impacted the experiment. And so although you can't conclude anything definitive from error bars, you can get an initial perspective on whether your experiment, the independent variable, impacted the dependent variable. Okay, so I know that that was a lot. We are stopping just before going into the CER format. Based on what you've watched, you should take notes and you should drop your questions on the new Jamboard that I've created and posted on the calendar that exists on Google Classroom for Monday, Tuesday. If you go to the top, it'll say daily plans. Click on that. All of these links will be active. You need to post your questions on the Jamboard when you're done taking these notes. This is typically something that takes us a little bit in class to understand and to get through. And there's trouble and misconceptions. And we go to practice it. We don't always get it right. So I am prepared for way more questions in this content than there was in the previous content. So post those questions on Jamboard, and I will see you all in class whenever I see you.